The extreme frozen landscapes located in the north of our planet, with its long hours of darkness for much of the winter, seem inhospitable to most. And yet, people travel from all over the world, here to the Arctic Circle, to see one of the world's natural wonders, the Northern Lights.
There's much more to the fantastic light show than meets the eye. I've come to the Norwegian city of Tromsø to find out more about this exciting window into space and hopefully catch a glimpse of the aurora too.
The brief window of twilight at midday soon fades, and we gear up to brave the cold on an aurora hunt. Our guide, Torsten Aslasken, is the perfect person to help. He's a former professor of aurora physics with a background in weather forecasting.
Torsten, hello, I'm Reya.
Hello,
Lovely
Reya.
to meet you.
Nice to meet you.
In this beautiful winter wonderland.
It is.
What's the plan of action?
The plan today is to go to a place called Skibotn. It's about 90 minutes drive from here. It's on the east side of the Lyngen Alps. It's a nice place to go for clear sky.
Is it an art or a science when it comes to predicting how likely we are to see the aurora?
Oh, I would say that is a very good combination of science and art, because the science is improving. We know more about the processes that gives the aurora, but we don't have that much of information about how the system actually is. So we are improving on how to predict the aurora, but it's still a lot of things that needs to improve further in order to have a very solid prediction of the aurora.
I'm incredibly excited about the prospect of us seeing the Northern Lights tonight for the first time for myself. Let's go.
Let's go.
As we drive out of the city, Torsten points out a small arc across the sky. And as we reach our location, it starts to intensify.
This is absolutely incredible.
It is.
Just illuminating the night sky.
We have had a really magnificent night with the aurora.
What are we actually looking at here? Can you explain what the Northern Lights are?
Well, what we are looking here is the green aurora. And the green aurora is there because there is an electron that just collided with oxygen in our atmosphere. When they collide with oxygen, they give the oxygen a little energy. And when these oxygen atoms jump back to the original state, they send out that energy in form of light. So these electrons that collided with oxygen atoms, they came from the sun about 2-3 days ago. And they went from the sun to the Earth with the solar wind. And when they met the Earth, they meet the magnetosphere. This is a volume around the Earth where the magnetic field of the Earth is dominating how these charged particles are moving. Most of these particles that collide with the magnetosphere, they just bounce off and goes further into the solar system. A few of these particles come into our system and they make a current system, a rather complex current system in our magnetosphere. One of these current systems dips down to the atmosphere, goes through the ionosphere and then out again. And when these particles enter the atmosphere, they make the aurora.
So what we're currently seeing in the sky is in some ways the result of the relationship between the sun and the Earth.
Yeah, it's an interaction between the sun, the solar wind, the magnetosphere and the Earth.
And it's an absolutely awe-inspiring interaction.
It is.
Solar flares and gigantic expulsions of plasma, known as coronal mass ejections on the surface of our star 93 million miles away, send out the huge clouds of electrically charged particles. Those that aren't deflected by Earth's magnetic field enter the ionosphere, the upper limits of Earth's atmosphere and the edge of space. The particles rain down over the polar regions, creating the aurora borealis in the north and aurora australis at the South Pole.
What causes the change in intensity of what we're seeing in the sky?
Well, there are a variety of factors that causes this change in intensity. First of all, the density and the speed of the particles in the solar wind. And this we can predict a few days ahead because we can see what comes from the sun. There is a key in the solar wind that can open up a door to our magnetosphere, and this is the direction of the magnetic field in the solar wind itself. If this is opposite to the Earth magnetic field where they meet the magnetosphere, then they effectively open up a door, then we can see a nice aurora display.
The result is a magical sequence of shapes, curtains of light, and what's known as a dancing aurora. The colours are caused by the particles interacting with different gases in the atmosphere. As Torsten explains, green is oxygen, while hints of purple, blue or pink are caused by nitrogen.
So much is going on in order for us to just get this beautiful illuminating light display.
It is. It's as long as the sun is sending particles to us and we have our magnetosphere, we can watch this thing. It will last for many years.
Just beautiful. The novelty never wears off.
It doesn't wear off, not at all.
It's not just tourists that are drawn to Tromsø. It's also a hub for space physics. Just 30 minutes outside the city is an international research facility which specialises in studying the aurora.
So welcome, Reya, to EISCAT Scientific Association in our Ramfjord Moon site here in Norway. And this is the core of our Norwegian operations here.
The EISCAT Scientific Association was established in 1975 and now has 6 member countries: Norway, Sweden, Finland, the UK, Japan and China.
Axel, it feels like I'm in the beginnings of a James Bond film with this as the backdrop. What is this?
So this system was the first system ever to be able to measure this kind of physics up in the ionosphere. So it's almost 40 years old. It started operating in 1981, and so it was the first time that we could actually measure the physics of the aurora in the ionosphere. And it has helped us a lot to understand what really happens up there.
How does the technology work?
Radar is radio detection and ranging. That's the core principle. So what we do essentially is we send a pulse which comes here through the waveguides, goes into the antenna, and then bounces off the reflectors, and then the parabolic dish will send the pulse up into the ionosphere, very short pulses, and then we listen to the echo from the ionosphere. So the electromagnetic wave from the pulse that we send up, it excites the electrons in the ionosphere, and then the electrons start wiggling, and then they send a signal back. And then we detect the signal, and from the time delay when the signal comes back, we know how far this pulse has traveled, and so we can work out how far up in the ionosphere we're measuring.
I know this site is vast, so can we see some more?
Yes, absolutely. Let's have a look around.
The radar system is used to study the ionosphere, which lies between 70 to 1,000 kilometres above us, so it needs a lot of power to transmit its radio waves.
So this is the Klystron Hall. This is the operational heart of the system, where we basically turn electric energy into electromagnetic pulses. This is where the magic happens here. So here we have capacitor banks in the high voltage system, where the capacitors, we use them as springs, so we charge them up with electric energy, and then we discharge them all in a very short period of time, and we channel the energy through the high power, high voltage system here into the Klystrons, where we then produce this electromagnetic pulse which travels through the waveguides out to the antenna.
They listen for the pulse's echo here, and at 2 other sites, one in Sweden and another in Finland. From what bounces back, it's possible to measure electron density, temperature, velocity and direction.
So there's a huge amount of data that you're receiving here, but what's the real world usage of that?
Well, it helps us understand how Earth's atmosphere is coupled to space, how space weather affects the atmosphere here on Earth. And the aurora is actually a reflection of what happens on the sun's surface. And then as the coronal mass ejection material travels through space and affects the Earth's atmosphere. And one thing that is important for, let's say, real world use is that when there's a lot of material coming from the sun, it will disrupt, for example, communications technology, satellites, geomagnetic storms. There's a lot happening up in the atmosphere. We have a very little amount of information basically on how the system, the ionosphere, the atmosphere works as a whole.
The ionosphere is a complex sea of electrically charged particles energised by the sun. Modern technology such as communication systems, satellites and power grids are all at risk from unpredictable changes in its composition and density, which can disrupt signals and damage hardware. The Arctic University of Norway in Tromsø makes the perfect base for inquiring minds to study space physics. Associate Professor Andres Spicher is looking at so-called turbulence in the ionosphere.
What does turbulence mean in this context?
So in this context, we study structures that are evolving and interacting highly dynamically, from very large-scale structures to small scales, where the energy is passed along the structures, and you see, first of all, worlds and structure interacting with each other. You could think of pouring milk in your coffee in the morning, where you start seeing small eddies and fluctuations moving around and very, very structured. So we have similar processes in the ionosphere causing different structures with different scale sizes.
Why are you doing this work?
So we're looking at that first because it's turbulence, and it's an interesting phenomenon that really hasn't been solved yet from a physics point of view. But also it has some application, what we call space weather applications, as the structures that are developing might affect signal from global navigation satellite services. So it can have some impacts on communication and navigation systems.
Andres has used the EISCAT radar to collect data on fluctuations and turbulence in electron density at different times.
So here we can see on this figure some of those parameters with respect to altitude and time. So in the vertical here you can see the altitude, and in the horizontal axis you have the time. So from about 7 p.m. until 10 p.m. we see how the ionosphere looks like from the eye of the radar.
What does the change of colour tell us?
From about 20 UT in the evening, then we see that we have an enhancement at about 100 kilometers altitude, very low, with some also electron temperatures enhancements. So it's hotter, and we see those enhancements which suggest that we have actually aurora just above the radar field of view during that time interval. So if we were outside, we would probably see some green aurora at that time.
What do these circles show?
So in addition to the EISCAT data here, there's also information about global navigation satellite system signals. And where you only see a small dot, it means there's absolutely no irregularities. But when you start seeing wider circles, it means that there's some fluctuations. So we see here, for example, we have one area where we can see there's a fast flow, fast moving plasma, and just on the edge we see a region where the signal from the GNSS receiver intersected some fluctuations.
The Sun has an 11-year solar cycle with an increase of sunspots and magnetic activity. In fact, we're approaching solar maximum in the middle of this decade, meaning more frequent and stronger solar storms. Particularly strong events will create beautiful aurora, but they can also adversely impact radio communications and satellites. On rare occasions, power grids can be affected, as happened in 1989, when the entire province of Quebec was hit by a 9-hour power blackout.
Now when we're coming to a solar maximum, we might expect more irregularities. So in the context of predicting also scintillations and irregularities, it's also useful to see this link with solar activity.
And how will you use that information?
So we'll use that information to try to better understand first what mechanisms are causing the structures, and then how, for example, the energy is transferred from the large scale to the small scale, if that's what's happening, and also to get information of the nature of the scales that are involved. And when we understand it better, then maybe in the future others can use to be able to predict will the structures affect the signals or not.
It's hoped that one day it will be possible to predict when and where global communication systems and technology will be affected by space weather. EISCAT associate countries all contribute financially and provide technical support. China's been a member since 2006 and has published dozens of papers, with more than 50 students having travelled to Tromsø to study. The EISCAT system has helped scientists gain vital information about what's going on in the ionosphere for over 40 years. But its ageing hardware is becoming more and more difficult to run. The two klystrons which convert electricity into radio waves have already outlived expectations twice over and could stop working at any time. With this in mind, EISCAT has something new in the pipeline.
The way that we do it here is, so we have a mechanical dish, we can steer it, but fundamentally it's quite slow. The movement of the dish mechanically is very, very slow compared to other technologies that exist nowadays.
A next-generation facility called EISCAT 3D is currently in construction. Before seeing it, there's time to meet a very special guest who's visiting from California. Dr. Douglas Vakich is president of the METI, which stands for Messaging Extraterrestrial Intelligence. The organisation is using the current radar for a purpose it was never designed for: to communicate with any galactic neighbours we might have.
One of the really sad things about a lot of technological progress is that when you get a new generation of technology up and running, you look at the older systems and you say, oh, we're not going to use that anymore. The beauty of working here in Tromsø is that EISCAT's going to be doing both. We can use the same transmitters, not just to understand our own atmosphere, but to send messages to nearby stars. So I'm interested not in the radio signals that bounce back, but the radio signals that keep on traveling at the speed of light.
How did you first learn that you could use this technology for different aims, to send your messages?
When we look for transmitters to communicate with the stars, there are only a handful of places that we can really do it. And one group of facilities are those that use radar either to track asteroids that are flying by Earth or to study our upper atmosphere. So EISCAT is one of the very few facilities that work for what we're doing. We approached them and they said, yeah, this sounds like an interesting experiment. Let's do it.
What messages are you sending out?
The real challenge when we communicate with extraterrestrials is to even figure out what language to use. I mean, they are not going to speak Norwegian or English or Swahili. So we have to come up with a language that is universal. And so we start with basic principles of math and science. Because if you're going to build a radio receiver on any world, you're going to have to know something as basic as 1 + 1 = 2. So those are the kind of concepts we use to start our interstellar messages.
In 2017, Douglas used the EISCAT radar to send their first message and is visiting again to work out the next line of communication.
How about the future? What are the future plans for the work you're doing?
In the past, there have been a handful of symbolic efforts to communicate with the stars. A message to this star, a few years later, another message or two to these stars. But there has never been a systematic search. The only way this project works is if we keep on targeting not just a handful of stars, but hundreds, thousands, eventually even 1 million stars. Because it may take that many in order to receive a star that has a civilization around it that's willing to reply. So it's really going from a demonstration that we have the ability to expanding to enough stars that we have a realistic chance of succeeding.
Will you be using EISCAT 3D for your work?
Now we've got a lot of technological advances. First of all, these systems are designed to just send a very brief code, but with the information-intensive messages we send, we need something that modern computing can allow us to do, that a facility like this can't. But even the very fact of shifting that dish from star to star takes time. With EISCAT 3D, it's instantaneous. You program it in, and there are no antennas to move. It's all done electronically. So that speeds up the process remarkably. And then, of course, the biggest issue is simply the power. Here we're transmitting with 1 megawatt, it'll be 10 megawatts, so much more powerful signals going out.
It's time to return to Earth and see what's being built in this wonderful winter wilderness.
Just take a look at this incredible view. We're en route to EISCAT 3D, to the site where we get the chance to view this world-first technology. It's 9:30 in the morning and still pretty dark outside. This is how it will stay for much of the day. Minus 15 on the temperature gauge, and really excited to get a glimpse of this new technology. Let's go.
The location for the new radar system is as spectacular as the drive itself, nestled in a valley surrounded by mountains.
This is the actual site for Skibotn, the EISCAT 3D transmit receive site. We have 109 containers arranged here in this hexagonal fashion, and each container will contain the electronics that we need to transmit or receive the signal. So each container is roughly a 20-foot long, and it has what we call the ground plane on top. And each ground plane then has 91 antennas fitted to it. In total here, 109 containers with 91 antennas is roughly 10,000 antennas.
How is what we're seeing here different to the previous radar that we saw?
So this radar is based on phased array technology. So rather than moving the old dish, remember, here we control the timing between antennas electronically with software. And by tuning the delay between one antenna and to the other, we can then shift the beam that we create. Shall we go upstairs?
Yeah, let's do that. Oh, wow. That's incredible.
Phased array radar technology is not new, but it's never been used on this scale before.
If we fire pulses from the two antennas at the same time, then it creates a sort of wave front which then goes up straight into the sky. But if we time delay this so that this antenna fires slightly before this antenna, then the pulse spreads a bit faster from this than from this, and that creates a sort of skewed wave front. So the beam created by all these antennas will then point slightly to that direction. So by simply changing the time delay between the antennas from one side to the other, we can tilt the beam from one side to the other. And that allows us to do really fast measurements in different places in the sky.
The old system could only transmit in one direction at a time. But with the new system, the antennas can be pointing at a completely different part of the sky within a millisecond. New facilities are also being built in Finland and Sweden, allowing measurements to be obtained from 3 different angles, enabling researchers to see the Northern Lights in 3 dimensions.
How significant are the possibilities this technology presents to our understanding of what's up there?
We will be able to do more accurate measurements. We will be able to, for the first time, do volumetric measurements of what happens in the atmosphere. This is a groundbreaking new instrument. There's no other instrument in the world like this. It's unique. It's really a quantum leap forward. But with all facilities, we don't know what the scientists are going to use in the future. So they might come up with completely new experiments that we've not even thought about until now.
Each hexagonal setup of container and antennas can be run independently. So while the majority are doing ionospheric measurements, others can be focused on something completely different. Associate Professor Juha Vairanen is an experimentalist with exciting plans for the new EISCAT 3D system, such as mapping the moon and tracking meteorites and space debris.
So space debris is yet another man-made environmental catastrophe that's unfolding in space. And it was first proposed by Donald Kessler, I believe in the 70s, that if you put enough satellites and rockets into space and they start colliding, each collision will create more debris, thousands of particles of more debris, now increasing the risk of further collisions. And you get a collisional cascade chain reaction that ends up just covering the whole space with debris.
There's an estimated 500,000 pieces of space junk between 1 and 10 centimetres in size currently floating in space.
If we can measure their trajectories and sizes, we can figure out what is the density of space debris, and that will give us information on being able to predict what will happen, how will the space debris environment evolve.
It could also help to develop methods to clean up space debris before it turns our nearest region of space into a no-go zone for future generations.
You must be very excited then about the potential for this new EISCAT 3D technology for your work.
One of the really exciting aspects is that we'll be able to get thousands of meteors per hour, hopefully, with this radar. And the radar is going to operate quite often, hopefully 100% of the time. And that will give us a catalog of millions of meteors. And hopefully somewhere in this catalog will be an interstellar meteor that comes from outside our own solar system. And we've never seen one before. There's no credible report of a meteor that comes from outside our solar system. This new technology, if we measure this 3D mass trajectory, it'll be a definitive proof that we've found matter that originates from outside our solar system and enters our atmosphere.
It's an exciting time as the radar nears commissioning.
How does it feel for you standing on this point after decades of work that's gone to get to this point?
Well, it's standing on the shoulder of giants. So there's many decades and many clever brains that have worked on this design here.
We couldn't resist one last chance to set off on a Northern Lights hunt, and this time we got very lucky.
You can imagine people in the past, when they were watching this, thinking, what is this? I mean, they had no clue about the real reason for it. But whenever they saw something in the sky, they kind of thought that this was either a message from God or dead people are waving back to us just to say hello to us. The aurora was also thought to have healing power, so it was something good, like a gift from the gods to us. And in some tradition, it's more like the aurora is something that you should be a little scared of. You should show respect for the aurora, and if you don't show respect for the aurora, it might come and take you.
Just look at that. It's like nothing you have ever seen before. A bright neon green, almost rainbow, haloing the sky above us. You don't have to see the Northern Lights to understand why humans have been fascinated by it, always, but it certainly helps. The illuminated night sky highlights just how much is still to be discovered about our place in space. But with the technological advances here in Norway, it seems we're closer than ever to the skies above and beyond.